I want to thank Savanes for inviting me here to give a presentation. And here is the outline of my talk. We will start with static multicriteria games and existing solution concept. And then we will consider multicriteria dynamic game with asymmetric players. First, we'll construct non-cooperative behavior and then cooperative behavior. Moreover, we will present a new approach to construct cooperative equilibria that guarantees the individual rationality conditions fulfillment. Then we will adopt the concept of dynamic stability or time consistency to multicriteria dynamic games. And to illustrate our approaches, we will see the example of resource management problem with asymmetric players. So mathematical models involving more than one objective seems to be more adherent to real problems. Players often seek to achieve several goals that can be incomparable. So those situations are typical for game theoretical models in economy and ecology. For example, in management problem, the decision maker wishes to maximize their production, maximize the profit and minimize the production cost. In environmental problems, the decision maker wishes to maximize the production and minimize the emission reduction cost, and so on. So multi-criteria game approach helps to make decisions in such situation. Shapley in 1959 presented the notion of static multi-criteria game, that is game with vector payoff of all players, and he gave a generalization of classical Nash equilibria for such game for two Pareto equilibria. Recent years, many authors have been studied static multi-criteria games, and some solution concepts have been suggested. In cooperative statement, usually the natural generalization of Shapley value is used in static multi-criteria games. But unfortunately, the concepts that are used in static multi-criteria game can be applied in dynamic version. So in our previous work, we presented some approaches how to construct non-cooperative and cooperative behavior in dynamic multi-criteria game. And I will show you a little bit later. But what is most important here that we will have an asymmetric setup of dynamic multi-criteria dynamic game. So usually the solution concept are presented under assumption that the discount factors are identical. There are some approaches how to construct cooperative behavior when the discount factors differ. For example, Breton suggested to consider weighted sum of individual payoff functions, and in continuous case the same had been done by Plot. And another approach was presented by Sorger. He used the bargaining scheme to construct the cooperative equilibrium. In our previous work, not on multi-criteria games, but on the dynamic games, we, with different discounting factors, we used the Nash bargaining solution to construct the cooperative behavior. What's the problem here? That if we have different discount factors, it's impossible to construct cooperative behavior summing up the payoffs of the player. So in our previous papers, we construct the cooperative behavior using the bargaining scheme with the sum of players' payoff. So under a symmetric setup, it's unusual to sum up the payoffs with different discount factors. And moreover, in our previous approach, the individual rationality conditions can be not fulfilled. That's why here we will present another approach to construct cooperative behavior. And moreover, it's very important to maintain the cooperation, especially in ecological problem. And that's why we will adopt here the concept of dynamic stability or time consistency. And we will present the payoff distribution, time consistent payoff distribution procedure. So I will start with the model. So we have, we will consider the big criteria game model with asymmetric players. So players differ in their time preferences. So they use different discount factors, and they exploit some resource and the state dynamics in the form 1. Here X is the size of the resource, F is natural growth function, and UI is the strategy of player I. And players wish to optimize two different criteria here. So the vector payoffs of the player are presented by 2. So we have an instantaneous utilities, and you see that players possesses different discount factor, delta 1 for player 1 and delta 2 for player 2. So first we will start with non-cooperative behavior, and to construct the non-cooperative multi-criteria Nash equilibrium, we will use the Nash products. So first we have to construct the guaranteed payoffs that will play the role of status quo points. In our previous work, we presented 3 variants how to construct the guaranteed payoffs. It can be as a solution of zero-sum games, as a solution of zero-sum games with weighted sum of criteria, and the third variant as a Nash equilibrium. And in this paper in 2017, it was demonstrated that the third variant is beneficial for player, and improves the ecological situation. That's why here we will adopt this construction, guaranteed payoff construction. You see that two first guaranteed payoff points will be constructed as Nash equilibrium in dynamic game with the first criteria of both players. And the second 2 guaranteed payoff points is a Nash equilibrium in dynamic game with the second criteria of both players. Next, we will construct the multi-criteria payoff function as a Nash product. So now the payoff function of each player is the product of the difference between their optimal and guaranteed payoffs. And here is the definition. We call the strategy profile multi-criteria Nash equilibrium if the next inequality are satisfied. So just like in standard Nash equilibrium, it's not profitable for players to deviate from the optimal one. But in this case, as you remember, they maximize the product of the difference between optimal and guaranteed payoffs. So we constructed the non-cooperative behavior. Then we will switch to cooperative one. To construct the cooperative behavior, we will also use the Nash bargaining constructions. At first, we should calculate the non-cooperative players' payoffs, which will play the role of status quo points. We can do it now. And then how we did it in our previous papers. We determined the cooperative behavior solving the next problem. So we maximize the product of the difference between the sum of cooperative and non-cooperative payoffs in both criteria. So the sum for 2 players. But you see that in this asymmetric case, we can do this summation. So because the players possesses different discount factors. So moreover, this approach does not guarantee the individual rationality. So it doesn't guarantee that each cooperative payoff will be equal or larger non-cooperative one. That's why we present a new approach, how to construct the cooperative behavior. So we will construct it as a solution of this problem. So you see that here we maximize the sum of the individual players' payoff. So it's similar to the classical cooperative behavior, when the players sum up the individual payoffs. But here, individual payoffs is the product of the difference between cooperative and non-cooperative payoffs in 2 criteria here. Yeah. So and under cooperation, they do it jointly, so they sum up their individual payoffs. And we call this solution a rational multi-criteria cooperative equilibrium. Why we call it rational? Because the individual, as I said, individual rationality conditions are very important. If the players' payoffs under cooperation is less than the non-cooperation, they will not come to a cooperative agreement, of course. So, and here we can prove that the solution of these problems satisfy the individual rationality conditions. So in both criteria for both players, the cooperative payoff will be larger or equal to the non-cooperative one. So this poses the players to cooperate. So we constructed the cooperative behavior, and as you see here, we can calculate the cooperative payoffs. So there is no imputation. There is no need to present some imputation distribution procedures. So we can calculate the players' payoffs for the whole game in this form, and of course, in similar fashion, we determine the cooperative payoffs for each subgame. Next, we will adopt so we calculated it, and next we should distributed among the time. So we will consider payoff distribution procedure. So here is the definition. We call the vector beta payoff distribution procedure for multi-criteria game if the next quality is satisfied. So the main idea is to distribute this cooperative payoff among the game path, and here beta I for each player is his payoff for both criteria, so with a vector. In extended form, those equalities looks like that. And vector beta is time consistent payoff distribution procedure if the equalities 9 are satisfied. Or in extended form, they look like this. So the main idea is that the players along the game path have the same optimality principle, so they don't have an incentive to deviate from cooperation. And we can present an explicit form for this asymmetric setup of the dynamic multi-criteria game, that this vector beta will be a time-consistent payoff distribution procedure. So you remember what we did. We calculated non-cooperative, we calculated cooperative equilibrium, and we presented payoff distribution procedure. And next I will show you the example, the resource management problem with asymmetric players with all those approaches. So consider B criteria discrete time by resource management problem, harvesting problem. We have two asymmetric players that exploit the fish stock over finite time horizon, and dynamics has form 11. So we have X is the size of population, epsilon is natural birth rate, and UI is the catch of player I. And players have two criteria to optimize. They wish to maximize their profit from fish sale and minimize the catching cost. And here we assume that the prices for the resource differ for the players, but the catching costs are identical, see, and depends quadratically on their catch. And you see that we have different discount factors for both players. So we start with non-cooperative behavior. First, we should construct guaranteed payoff points. As you remember, it's a Nash equilibrium. First guaranteed points is a Nash equilibrium with the first criteria of both players. We can do it, and the guaranteed payoff will take this form. And the similar for the two second guaranteed payoff points is a Nash equilibrium in dynamic game with second criteria of both players. And now to construct the multi-criteria Nash equilibrium, we solve the next problem. So for each player, we maximize the product of the difference between his optimal Nash equilibrium and guaranteed payoffs. And considering this process starting from one stage till M stage game, and we seek the linear strategies, we can construct it in this form, and the player strategies at the last stage can be determined from those equations. Not very small. So now we can calculate non-cooperative payoff because we will use them to construct the cooperative behavior. So to obtain the rational multi-criteria cooperative equilibrium, we solve the next problem. So we maximize the sum of the product of the difference between cooperative and non-cooperative payoffs for both players for both criteria. And again, considering this process starting from one stage till M stage game and seeking linear strategies, we get this solution, and the player strategies at the last stage can be determined from this equation. We can see asymptotic dynamics. So when it's in the non-cooperative case, it's in cooperative case, and as you see in both cases, in asymptotic, when times t tends to infinity, the size of the resource tends to the initial one. And the only difference is how to distribute it. So it's distributed proportionally to the player's strategies on the last stage. And we can construct the time-consistent payoff distribution procedure here. It will have this form for both players. And I will show you some pictures. So here is the population dynamics. So duck is the cooperative one, and light is a Nash equilibrium. You see that cooperation here improves the ecological situation, so the size of the research is larger. And also it's more beneficial for players to cooperate, so their player strategies, their catch is larger too. So here is some conclusion. So what we did, we considered the asymmetric discrete time game model with two asymmetric players with two different criteria. And first, we constructed guaranteed payoffs and multi-criteria Nash equilibrium. Second, we present a new approach to construct the cooperative equilibrium that guarantees the fulfillment of individual rationality conditions. And third, we adopted this concept for dynamic stability concept for dynamic multi-criteria games and construct time-consistent payoff distribution procedure. So here is some literature. And thank you for the attention.
Let us thank the speaker. Thank you. So now it's time for questions.
Yes. So I think your work is very different, but long ago, I think in the early 80s, there was work done on fishing by people, including Len Merman and Rabah Amir and Len Merman. Are you familiar with that work? It may be.
Sure. Sorry, one more time. The names?
First.
Not Rabah Amir. It was.
Let me spell the name, Yair. Amir is the first author's last name. And the second one is Merman, Mirman.
But before that, Pradeep, there was a paper before that by David Levhari and Len Merman.
Okay, so
that's called The Great Fish War.
The Great Fish.
Yeah, of course I am familiar, and I have some previous works on this fish war problem. So Levhari and Merman and later work, they consider the model fish force model. So it's very, that's why I use it, because it's very easy in this model to construct the solution in analytical form. So it's good for consideration. So I have a lot of works on this model too, but here it's completely different because there is multi-criteria.
Okay. Can you show the definition of Shapley for the multi-criteria? Yeah, that page, the page where Shapley's definition.
Yes, of course.
It went too fast.
That's okay. It's here.
Okay, one second.
That's here. So the Shapley is non-cooperative game. So we have a set of players and a set of strategies, and the payoff function of each strategy is the vector function you see here.
Right.
Vector function. And here is the weak and strong Pareto equilibria. So it's similar to Nash equilibria, but in vector form, you see? That because those inequalities should be in vector forms.
So UI is a vector. Is UI a scale? UI of whatever is inside the parentheses. That's a vector. Or
yeah, it's a vector.
Yeah.
So this is, I see. So it means simply that you can't deviate to weakly or strongly Pareto improve among the different criteria.
Yes. But in vector form.
I understand. Yeah.
Mm-hmm.
So, so if you take a special, for example, take a weighted sum or take the product of the utilities and use that as a scalar payoff function, if that Nash exists, it will also automatically be a Pareto, a multi-criteria Nash. So you can generate many multi-criteria Nash by creating lots of different payoff functions, right?
I don't see maybe.
I'm saying you can convert. You can create artificial payoff functions. For example,
yes, of course.
Weighted sum or product of the components. And for any of these, you can if you can find Nash, it's also a Nash in the sense that Shapley has just defined it.
Yes, because the commonly used solution, this is not a very used solution concept for static multi-criteria game. Usually they scalarized the payoffs, so they maximize the product, the sum of the weighted sum of criteria.
This indicates that there will be a great multiplicity of such equilibrium. Because for every scalarization, you will get some Nash easily, often.
Yes.
And so there is a huge number of such Nash equilibria, multi-criteria Nash. It over exists.
You mean my approach or this static
I'm
approach?
thinking in general. So I wonder if there is some selection criteria, because there is clearly over existence.
This is a game without side payment.
I understand, but you can pretend side payment, and anything you compute will satisfy Shapley's.
Yes.
So by pretending side payments and looking at any monotonic function of the n variables, n criteria, you can then scalarize it artificially, compute its Nash. Okay, there's no side payment in Nash. Everybody has his own payoff function. Yeah, everybody is creating his own payoff function. They are not transferring between each other, but they are converting multi-criteria to a scalar payoff, and no side payments. They compute Nash, and they can do it for any weighted sum, any product, any scalar function of. Everybody is creating his own artificial payoff function, and you compute Nash, and it will satisfy Shapley's criteria. So I'm saying, unless I'm missing something, which I always do, it seems there will be huge over existence of Nash. There will be too many Nash, like a folk theorem. And the question is, what do you do with such a situation?
You go to refinement.
Yeah, so I'm asking, is there a refinement here, or what happens?
Sorry, what is the refinement?
Meaning
Future work.
selection. There are so many Nash, that multi-criteria Nash, how do you pick which one you like? That's
like in regular non-cooperative games where you have perfect equilibrium, subgame perfect equilibrium, proper equilibrium. So you start refining the concept to nail down, hopefully, one. Typically,
but I'm asking, what are the criteria that you could use here? I don't know. I mean, I'm just asking. I don't know the answer. Anna, I don't know the answer. I'm just
okay.
As they say, any fool can ask questions which 20 wise women cannot answer. So I'm just.
I believe that also Pareto equilibrium cannot be unique here.
Right. I agree. It looks like a folk theorem effect.
Well, this arises even in the single optimization, vector-valued optimization problems. If you have just a single decision maker and there are multiple criteria and you want to satisfy all of them in the Pareto sense, then as Pradeep is saying, any sort of, you can convert it to a single objective function, either through a convex combination or a product. So you'll have a continuum of solutions, even in a single person decision-making problems. And sometimes what people do is they say, well, let's put equal weight on these. That's one way of selecting, narrowing down the number of possible solutions, or other considerations may come into picture. And that's the refinement of the Pareto optimal.
By the way, when they take equal weights, it is totally arbitrary, but they give it a very nice name. They call it egalitarian. As if by using the name, we can be brainwashed into accepting it.
Sure. No, but I'm not necessarily defending it. I'm just saying that that's one way of narrowing down the.
I know, you are exactly right. The problem is there with one person problem. Forget games.
Right.
You are exactly right.
Okay, thank you. I should think.
Other comments or questions? I believe that there some references are missed here. For example, the next speaker, who is Jesus Marin Solana, I know that he has a lot of papers with different discount factors. So you didn't mention him, so but in an hour he will present something, so be prepared. I don't know what he will speak.
Yeah, I know.
Okay. Yeah.
Okay, thank you. I have a short question. for the IDP, whether there could be another way to define IDP so that the solution is time consistent. But it's
There is no
maybe
IDP. Here is the payoff.
PDP, sorry,
PDP,
PDP,
yeah.
PDP.
Another way.
Yes, you presented one way. It's a kind of sufficient condition, right, for the
Yes.
PDP. What could be, for example, what is the possible way to do it for the phishing problem? Or
You
maybe,
mean how to do it in reality?
yes, maybe. Or what is the possible way to do it? Because usually people define it as a difference, as a difference for each time instant. But
You see
according
it
to
here.
definition,
You see here that there is a difference. So we proved that this vector, the difference, discounted difference, is time consistent.
yes, but could there be any other way to define IDP so that it could be time consistent?
I don't think so, Amanes.
For example, will it be possible to put all IDP into the end of the game and pay it at the very end of the game? And will the solution be still time consistent or not?
No, because we use here the, you see Nash bargaining solution, and it's not time consistent. So we should distribute.
Okay, maybe I'm mistaken. Usually if we consider the transferable utility game, for example, dynamic case, then we can define IDP or imputation distribution procedure in the way that it is paid at the very end of the game. Will it be time consistent, right?
No. If the solution concept is time consistent, then it will be. But the Nash bargaining solution is not time consistent.
Okay. Okay, it's clear. Okay.